Hello. We want to uh, discuss mass correction of a spring. Um, when a block of capital mass M is attached to a spring of small letter m mass, a spring constant K sub s, and so the length of the spring is L. We usually don't need these and this in introductory physics because we assume the spring is massless compared to big M, and any energy that goes into moving the spring we can just ignore it. We just look at the energy of mass M. We're gonna try to correct that. We can see how to have this little m a roll into the frequency that we'll observe. Okay, so how do we do it? We use the longitudinal motion of the spring. This is like the longitudinal motion of a bar, vibrating bar. So it will look very similar. Our task is to find the frequency, not just one frequency, but the lowest frequency at which this system will oscillate. So we're trying to find a normal mode of this system, and normal mode of the lowest frequency. So of course it will have infinite number of modes. We just want the normal mode, the lowest frequency mode. Okay. So we look at a small piece of a spring. When the spring is, say, in a stretched state like that, this point of the spring will be over here, and this other point will be over here. So if you see that the spring now has it has this new length. This used to be this length, has a new length. So delta x has gone to delta x plus delta psi. So this is the amount that a spring has stretched, and we want to figure out the tension force, or spring force, or tension force that will be here at this point. So the tension force will actually vary along the position of spring, and we use the x-axis to actually locate the position. So how do I figure out this tension that this tiny piece of spring will feel at this instant? Well, it used to have delta x, so you can think of this as I have a spring of length this that is stretched by this. So we like to figure out what the force will be, but we need to know what the spring constant. So clearly it will be whatever the spring constant of this, let's call it k of this delta x, this spring, which I have the two terms here. For that spring, I know for the longer spring, the spring constant k sub s. Well, how do I figure this guy? This is not k sub s, first thing to notice. And why is that case? Well, you can imagine the spring as the full spring is made of all these springs in series. This is the full spring length L. It's made up of springs in series, and one of them is the spring. This is the one I want. Well, how many, if I just had two of them, you can figure out. So suppose I had just two springs and they were in series. So this is say K k is small, so k prime, so k prime, and this is k prime, and the whole thing is k, and each one is length over 2 or length over 2. So what is the relation of k prime to k? Well, when the springs are in series, they add in a different way. It's different, so it adds like 1 over k prime plus 1 over k prime is 1 over k. So if I have two equal parts, then k prime 2 over k prime is 1 over k, so k prime is equal to 2 times k. So amazing, the spring constant twice as much. So now with delta x, the number of pieces I will have will be L over delta x. That means the spring constant k delta x is actually n times k sub s. K sub s is the for the whole thing. Here I wrote k, let's call it k sub s, k sub s, k sub s. Okay, so if I have, this is the spring constant, then t at x, this is just arbitrary instant, that should be equal to k delta x delta psi. This is the additional stretch I got. So that's the magnitude, and you can write down L over delta x times k sub s delta psi. You can see that these in the they can go together, LKS delta psi over delta x, which in the infinitesimal limit will look like L k sub s d psi dx. So this is going to be the tension. You can analyze the forces now. That's going to be varying on across x. So if I have got that delta x, this is at x and this is at x plus delta x. So there will be force pulling that way, with tension x plus delta x t, and there will be force pulling this way, tension at x t, and the net force will be the subtraction of this. So this is the x direction. So net force will be equal to F net equal to T x plus delta x minus T x t, and we can you can see that if I just divide this by delta x and then multiply by delta x and take infinitesimal limit, I get dt dx dx, and then this is equal to, just say I'll use this, and this will be L ks d square psi. I can just leave this guy alone, just take a infinitesimal limit in here, d square psi dx squared delta x. So this is the force on this piece. So I got this piece, and I got the net force is this amount. And so if I know what the acceleration is, so this should be equal to mass of this guy, let's call delta m, times acceleration. So I got L ks d square psi dx squared delta x. So that's the force, and I'm on the right, equals ma will be delta m times the acceleration of this thing. So delta m, what's the delta m going to be equal to? It's going to be however mass there is a mass distributed over length L times delta x. So that's going to be, and you can see the delta x will cancel out, and that was an arbitrary, so cancelling out is a good thing. What's the acceleration? Well, delta psi is the displacement. So the velocity of this delta x thing is d psi xt dt, and so acceleration of this delta x thing is d square psi xt dt square. So we have L ks d square psi dx square delta x equal to m over L delta x d square psi dt square. So delta x cancelling out. So it seems, it appears that we have a wave equation here, a classical wave equation that is obeyed by this system. So this L goes down here, m ks L square d square psi dt square, and this should have units of 1 over b square. So this is equal to 1 over b square d square psi dt square. So we need to solve this equation and with boundary condition, solve with boundary condition. So what are the boundary conditions here? Well, boundary condition will be at the very left end. So boundary conditions on the left end, we are going to get on the left end going to get psi at 0 at all time should be 0 because support is fixed support. On the second end, when I go over there, that is going to be equation of at that point is mass acceleration of that guy, and we should get mass d square psi at L dt squared. So this is the equation of motion of the block. That mass accelerate the block should be the force on it, and force should be pulling in minus k ks L d psi dx at x equal to L. In the next video, we'll talk about how to solve this and what the solution of this thing looks like. So this is setting up the problem, and solving this problem will be in the next video. So let's call this set up part, and maybe this is video 1, the 2-part solution to mass correction of a spring. Okay, so see you in the next video.